Hello everyone. Today we'll try to we'll discuss another most interesting question that I was asked in a PhD interview. So the question was why baryon number is conserved in a particle interaction, not meson number. We will first try to answer what is baryon number. Then we will understand what are compute baryon number for various types of particle like baryon, hadrons, baryons, or mesons, and anti-baryons. And then we'll see what are the possible cases in a particle, what are the possibilities in a particle interactions, and try to understand why baryon number must be conserved. And then we will understand why proton cannot decay in the standard model of particle physics. So what is baryon number? Baryon number is defined as the one-third of total number of quark minus total number of anti-quark irrespective of their flavor. Flavor means quarks comes in different flavors like up type, down types. These are different flavor of a quark. So let's compute the baryon number for baryons. Baryons is a bound state of proton, 3 quarks. For example, proton is made up of 3 quark, 2 up type and a down type. So total number of quark is 3, total number of anti-quark is 0, so baryon number is 1. Similarly for neutron, lambda, baryon, the baryon number is 1. In case of anti-baryon, for example antiproton, which is a bound state of 3 anti-quark, the total number of quark is 0, anti-quark is 3, so baryon number is -1. In case of meson, which is a bound state of a quark and anti-quark pair, so the baryon and so total number of quark is 1, anti-quark is -1, so the baryon number is 0. So let's understand what are the possibilities how quark number can change or anti-quark number change in a interaction. So according to the standard model, which is the best model which describes fundamental particles and their interactions, it includes 3 out of 4 fundamental interactions: strong, electromagnetic and weak interactions. In strong and electromagnetic interaction, it could possible that quark antiquark created or annihilated in particle-antiparticle pair. What will happen? How the baryon number will change, or the net quark number minus net antiquark number will not change, because this will create there will be an increment a particle pair, particle and antiparticle pair created. Then there will be an increment of quark number and increment of anti-quark number, so the difference will not change. Similarly for annihilation, particle antiparticle annihilation, or other possible, it is that only quark going to another quark, or let's say in weak interaction, quark could change its flavor, let's say from going from up to down with the double boson, but the quark number here is not changing, and it could possible that up u bar d bar, for example here Proton Decay, could annihilate to give a double boson. Here also the difference is not change, will not change. So there is, what are the possibility? It could possible in an interaction particle antiparticle created. For example, here there are particle antiparticle creation, here a particle antiparticle creation. But there is no way that a single quark or a single antiquark created from a vortex. Because of this, net quark number minus net antiquark number will not change in an interaction. Because of this, the baryon number must be conserved in an interaction. Now let's understand why proton cannot decay in the standard model. Let's say proton is decaying to particle A and particle X. And in this case, energy conservation of energy and momentum conservation requires, you can compute for the two-body decay. The mass of protons should be greater than equal to mass of particle A plus mass of particle X. Now here is the part. Baryon number conservation requires that there must be, since proton is a baryon with baryon number 1, so there in the final state there must be a baryon, either A or X is a baryon. Let's say A is a baryon. Another fact, proton is the lightest, so A must be heavier than the proton. So this will not satisfy this conservation, energy conservation, momentum conservation relation. So therefore no allowed final state consistent with both baryon number and energy conservation. Because of this, proton decay is forbidden in standard model of particle physics. Thanks for watching.